I think in science, complexity is still appreciated when simplicity should be what's appreciated. The Americans, somebody has an idea and everybody says, oh, that sounds interesting, let's try. Here, somebody has an idea and everybody comes up with 100 reasons not to try. Right? And you just have to try.
Welcome to the third episode of the Thinkers and Makers podcast. This is a conversation I had with Oliver Brock. Oliver is a professor of computer science at the Technical University of Berlin. He's a world-renowned figure in the field of soft robotics, which I think is one of the most exciting disciplines of computer science or like engineering in general. I hope you enjoy the podcast. If you do, please like the episode, subscribe to the podcast, and now, please enjoy my conversation with Oliver Brock. So Oliver, we're here now back where it all started at TU Berlin, where you're currently a professor. But you also studied here, computer science, in your bachelor's. Tell us what inspired you to study CS.
Well, first of all, it wasn't a bachelor's. Back then, we didn't have bachelor and master's. It was a diploma. This is a long time ago. I started studying computer science in 1988. And the reason why I studied computer science, actually, I studied computer science and physics together at the same time. Because I thought computer science was good for getting a job, and my interest really was physics. And I realized that both of this was too much to do at the same time. And so then I decided to go for the breadwinning option, computer science. But I think in the end, that was a good choice because it led me to, I think, a field that's super, super interesting and that is relevant and shaping the future, right? Not just relevant to the future, it's actually shaping the future to a large degree.
I love that. I also think it's super interesting that you studied two things. My very first guest on this podcast, Daniel Kremers, also studied mathematics and physics, so he also did 2 degrees. So that's very cool. That's something I'm kind of sad about, that very few people in the bachelor's master's system that we have in Europe currently dare to actually actively pursue 2 fields at the same time. I think that can be
well, at least initially. I think that's a good idea, right? So I didn't finish, just to make that clear. I didn't get my degree in both of these degree programs. But I think in general, to take classes in other study courses is excellent. I also took courses from philosophy and art history, and I think that was a very nice complement to computer science. So I could only encourage people to try to explore what a university has to offer.
That's super cool. We're soon going to get to your time in the US, but maybe one question kind of before that is also very related. In the US, they do a lot of liberal arts programs where you can basically, for 1.5 years, take courses from a wide range of topics, and then later on you specialize, but you still have the freedom to take courses from all kinds of disciplines. And that was originally a European idea, but then we kind of stopped doing it. Do you think maybe we should reintroduce liberal arts in Europe?
Well, I think this is actually kind of happening to some degree, in the sense that we have now, for example, at TU Berlin, a study course that's called MINT Grün, where within the engineering disciplines, people can take courses from all the different disciplines, and then in the end, or after 2 semesters, decide which specific study course they want to pursue. Clearly, this is not as broad as liberal arts, but maybe to just answer your question straight away, right? I think yes, we should. I think it's not just a way of starting your studies without knowing what you want to do, trying things out to make up your mind. I actually think it's super important education for everybody in a democratic society to be exposed to this variety of topics and to start thinking about our world from different perspectives. So I think we should not just train people that later on take professions, but we should train people that become members of society.
Cool, yeah, I fully agree. So then you studied in Berlin for your diploma in computer science, and then you went to Stanford to pursue a PhD.
Yeah.
How did you get from Berlin to Stanford? What inspired that move?
Well, I think the short answer is laziness. So I actually didn't know how to pursue a PhD, which is very strange and embarrassing to admit now. But I thought that what had to happen was that a professor asks you if you want to be, their PhD student, and nobody had asked me during my studies. So I thought, okay, that's not an option anymore. Now I have to take a job, and to me that meant getting up at 7 in the morning every day, and that didn't seem very attractive. So then I heard of two friends. They had applied for a scholarship to go to the US, and I thought, well, if they do it, why shouldn't I try? And so I applied, and I got the scholarship. And yeah, I had no idea that Stanford was a good university. I went to the library. Back then there were still libraries, and there was an aisle with computer science conference proceedings. Back then, a couple of aisles were enough for that. And I just browsed through some proceedings to find a paper that I thought was interesting. And I found one that said Stanford, and I'd never heard of Stanford before, but it said California. I was like, okay, how bad can that be? And so I applied for the scholarship for a particular project to be conducted at Stanford, and I got in. And then I realized, oh my God, I've gotten really, really lucky. Yeah, that was really a big coincidence.
Wow, so you kind of on accident got into Stanford. That's very interesting.
Yeah.
Cool. And then the project, tell us about the project. What did you do there?
The original one?
Yes.
So I found a paper by a professor called John Koza on genetic programming, that is taking the idea of evolution and applying it to source code. And I thought that was very fascinating. And so I wrote a project to the DAAD, the German Academic Exchange Service, about evolving genetic subroutines, so code subroutines, but using evolution, how one could go about that. And so that's the first project I did. As a matter of fact, it's the first kind of paper I wrote way back when, long time ago.
Cool. And that was also the PhD project that you ended up working on?
No. There lots of things happened in between.
Many things.
After that, I stopped really doing these evolutionary things, and I started to get more into robotics, which is something, my diploma thesis here was on robotics. And so, I started basically working together with a professor who, his name was Osama Khatib, who ended up being my thesis advisor.
How did you get in touch with him, and how did that evolve? Did you seek out someone who did robotics because you wanted to go back to that field, or?
Yeah, so basically somebody told me that all research groups have weekly meetings, and that if you ask to participate in these meetings, people would sometimes invite you to come. And so I did. I contacted the professors, and in retrospect, I think actually that was kind of bold of me. I don't know of anybody else looking back who did that, but I did it, and so I attended several people's research group meetings for a while, and then kind of things develop, right? It's not like, I don't think it was sort of a real decision. It one thing led to another, a conversation led to an idea, and then I tried something out, and but then I converged to my advisor, Osama Khatib.
That's cool. I mean, we again see that you did quite a bit of like surveying. You looked around, checked out a few groups, and then decided for the one you liked the best. You found the most interesting.
Yeah. And some things I was systematic, and then others just tried one thing and got lucky.
Yeah, cool. So then, what happened later? PhD work, and yeah. So what did you do in your? What's the main focus on your PhD, and what happened after? Why did you go into academia? Why did you decide to do that?
So my thesis topic was about the integration of, if you want, control or execution of robot motion and motion planning. These were two very separate fields, even though they really deal with the same thing and are two sides of the same coin. And in my thesis, I tried to develop algorithms that kind of linked these two areas. Well, I didn't just try, I also did it. So yeah, I developed some algorithms that bridge that gap and thereby took this idea of motion planning and made it more practical in the sense that you could now execute motion plans in dynamic environments with people and so on. Yeah. So that ended up being my thesis topic. And after that, it was kind of clear to me that I wanted to stay in academia, and I applied for postdoc positions. And I got an offer from a professor called Lydia Kavraki at Rice University in Houston, Texas. She had been a postdoc, she had been a PhD student, I think, even at Stanford, while I was also a student there, so I already knew her. But then a friend of mine from Berlin, actually, who I by chance met at Stanford, wanted to start a company, and he was a business person.
So also had a background in business? Or?
He originally was an engineer, I think an industrial engineer, and then went to Stanford Business School. And then, it was his idea to start a company. And so he, in the Silicon Valley, if you want to start a company, you need somebody who smells like technology. And so he, was trying to lure me into it. And I said, I want to really be in academia, and I'm happy to help, of course. And then they actually ended up getting a meeting with venture capitalists and said, Oliver, we need somebody to talk about technology. Can you come? It's like, okay, I'll come. And then I, stood there talking about web service and things like that. And yeah, before I knew it, I was CTO of a company. And I don't really recall a moment where I said, okay, I'll do it. It just kind of happened.
And that was also your full-time job then?
No, I actually commuted back and forth between Houston and San Francisco.
Okay.
That was, I think at the height it was once a week I was flying back and forth. This is a long time ago, so there was not so much concern about CO2. Everybody at the airport knew me by name, so that got old very quickly. I did that for 9 months.
And what did the company do?
The company was called alladvantage.com, and the tagline is infomediary. In effect, it's what everybody is trying to do, right? It's making money off of data, except that we were trying to do that from the other side. Google, Facebook, Apple, Amazon, all these people are making money using the data that you have in one form or another. And it's the data that the consumers, the people produce, but it's these companies that make money with it, and they give you some kind of service in return. We took the other approach. We basically said we're on the side of the consumer. We're going to monetize the data for the consumer, but we're going to protect your privacy. And we're going to let you have control over how and for what we use that data. Plus, since we're now kind of like a consumer union, right? We're defending the interest of the consumers with respect to large corporations. We can also negotiate deals, right? We can say we have 2,000 members that want to buy a new laptop. What kind of deal are you going to offer for access to these members? And then and we did this actually back then. And our members got money. We took some transaction fee of that transaction. They protected their privacy, and I think it's still a really, really good idea. It's just very difficult. We were very close to actually succeeding, and I think the internet would be a different place if we had succeeded. But we were 2 weeks away from going public, and raising like 600 million dollars. That would have carried us on for a very long time. But then the internet bubble burst. And for 2 years, no internet company went public. So that kind of messed up our plans.
And did you leave when kind of the bubble burst and the SAR was over, or did you leave before that?
Well, no, actually, when the bubble burst and things got tough, I left Houston, left Rice University to come back full time. I was a founder of the company to kind of help the company as much as I could. But then at some later point, there was we basically decided that the founder should leave and let some other people take over. We had hired a very seasoned CEO. We had a very seasoned person as a CEO that had a very high VP job at Hewlett Packard, and just an amazing person. And so we let them take over, but the internet bubble, the internet dip was extended in time, and so it didn't work out.
So that was the end of your career as a startup founder.
Yes, I guess you could say that, even though I still have the obligatory foosball table, which is actually standing in the robotics lab on the 5th floor, and the people play foosball.
So more of a professor, but still the startup energy. Then you after you went to after Houston, you went to UMass Amherst. Yeah. Is that correct?
Yeah. So actually, I first went back to Stanford. I worked as a consultant for a little bit, and I also went back to Stanford as a postdoc. Mm-hmm. And while I did that, I applied for jobs in academia. Mm-hmm. And the only job offer I got was one from UMass Amherst. Mm-hmm. So I ended up going there, which was a great place. Mm-hmm. I really think that UMass Amherst is a fantastic place, and it was a tremendous environment for a young faculty to start out and build a research career. It was very supportive. People were extremely nice and helpful. Mm-hmm. So I mean, I can only say the best things about that. Again, it was a complete coincidence, right? Mm-hmm. I've only ever heard that other universities are kind of cutthroat and, big competition among people. UMass Amherst was fantastic, and I think it really also influenced, mm-hmm. the path that I took as an academic.
And then Amherst prepared you for the return home, back to Berlin.
Yeah.
How did that happen, and also how did it feel like coming back home after so many years? And I imagine the culture in California or in Massachusetts is quite different from the culture here in Berlin.
Yeah. I mean, I always wanted to go back. I spent 16 years altogether in the US. Mm-hmm. The first of that was the scholarship from the German Academic Exchange Service. And I wanted to come back the whole time, and I actually tried again and again to come back. But it was always that in the US, I got better job offers faster than I could get them in Germany. Mm-hmm. And so I ended up staying for 16 years. Mm-hmm. But then the position here at TU Berlin, where I had written my diploma thesis, mm-hmm. Opened up because the roboticist from whom I had learned my first robotics course retired. And so I obviously applied to it, and I got invited, and came here and presented and discussed with people. And then the Alexander von Humboldt Foundation announced a new funding program that was designed to bring researchers from other countries to Germany, and that was called the Alexander von Humboldt Professorship. Mm-hmm. And my former professor, Professor Hommel, actually suggested that we apply for this, and we did. And again, I was incredibly lucky mm-hmm. to get that. And so then that was the sweetest deal in the world, right? I could get home to my home country, right? I could become a full professor, mm-hmm. and I would have 5 million euros startup funds. So that was a now or never deal. It would never, ever have become better than that. Mm-hmm. So, I decided, well, actually it wasn't a decision. It was obvious that I was going to do it. There was no decision involved. And yeah, I remember walking down the streets, by myself the first time after coming back, knowing I now live here again. And I remember feeling like coming back home from a vacation after 3 weeks. It's like, yeah, this is home. Exactly. So it was really, it felt very natural, and I never regretted coming back. And I miss people in the US, but I miss the academic environment because that's, very well organized and efficient. But as a person, I think it was great to come back.
What's like one thing we can learn from the American academic environment, or maybe one thing you try to take back home from the US? One insight.
If there's, I think the number one thing is, well, there's so many.
You can also give us many.
Yeah. So I think number one thing is the Americans, if somebody has an idea and everybody says, oh, that sounds interesting, let's try.
Mm.
Here, somebody has an idea and everybody comes up with 100 reasons not to try.
Mm.
Right? And you just have to try.
Mm.
Right? Change is part of life.
Mm.
And so I think we have to continuously try out new things. And so that is very frustrating, that it's super difficult to change things here. And people are afraid of taking responsibility and of trying things out. And so I guess it's kind of the entrepreneurial spirit, right? I mean, just, there are risks. This could go wrong. I'm going to do it anyway, because I think it's a good idea, right? And I wish we had more of that in this country.
Yeah, no, I agree with that assessment. I agree very much. So now in Berlin, you're part of the so-called Science of Intelligence cluster, which seems to be another big research grant you got, or you managed to get with a group of other researchers. Could you start telling us about the motivation, the scientific motivation? What's the project? Who are the researchers? What are their backgrounds? And why do you want to do that project with these researchers? What insights are you hoping to gain?
I think the starting point is something we all realize, that when we interact with computers and when we interact with humans or even animals, there's something very, very different. Mm-hmm. And I don't mean that, computers don't breathe and things like that. I mean, animals' biological intelligence is just so much more flexible, adaptive, inspiring, and look around the things that we've done as a species. Some of them are horrible, but we've also really invented quite a few incredible things that help a lot of people. So what is it that made us do that, right? We understand of black holes and red dwarfs and quarks and galaxies and Big Bang, but we don't understand what it was that allowed us to gain access to that understanding, which is ultimately what we call intelligence. And so I think that's one of the last big enigmas of humankind. What is it that we do when we use our brains and our bodies? So I think that's a big scientific question in itself. And then maybe another question you could ask is, well, why do you think that you or roboticists or the people that are there are the right people to figure out what the answer to these questions are? And I think what we've done here is we've assembled all the people in Berlin that study aspects of intelligence from any kind of perspective, right? So we do computer science, vision, robotics, machine learning, AI. All of these are obviously aspects of what we call cognition or intelligence. And then on the biological side, biologists, behavioral biologists, psychologists, neuroscientists, but also educational science, right? Because that's also an aspect of intelligence that we need to learn, right? When I cannot build a 747, nobody actually can, but as a group we can. So social interactions are important, culture is important, language is important. All these things, and we don't yet study all of these, but we were starting from a simpler baseline, but we're going to try to move towards that in a hopefully second funding period for this cluster.
How long are these periods?
So it's 7 years, and you can apply for, I think, up to 60 million euros.
That's a lot of money.
It's a lot of money, but there's also, I think we're over 30 professors.
It's a big group.
It's a big group. There's about 160 researchers, PhDs, postdocs, and student assistants. So it's a big endeavor. But what we are learning is that putting all these perspectives together actually really creates interesting insights. It creates interesting questions, and it trains people in really what I find to be very amazing ways. I mean, there's a roboticist that is completely conversant in, in psychology, right? I mean, they not that they're psychologists, far from it, right? But they can have a conversation. They understand the motivation of the field, the general methods, the way of thinking about problems. And I really think that having this community here, united in this one building, really creates an interesting new twist to science.
How do you coordinate research across so many people? Do you have like reoccurring meetings where everyone's present and you just like toss around ideas, or does one person or a small circle set an agenda that everyone has to follow, or how does that work?
All of the above, I think. I mean, so research, you cannot really micromanage research, right? You need to give people space to develop their ideas and to pursue them. But the cluster itself, this research center, imposes some rules. So, for example, we have 4 different funding programs, if you want. We call them research units. And if you want to get money in one of these research units, you have to present research of a certain type. So, for example, one of these research units is about generating intelligent behavior. And so you have to tell us what is it that you want to generate, and you have to combine perspectives from biology and perspectives from computers, basically. And you have to explain how they will interact so that you can advance towards an understanding of what is that behavioral target, how can you synthesize that target. And so that's an overarching structure that was imposed at the time of writing the proposal that now people follow. And I think, some of these ideas have proven useful, some of them have proven not so useful, but we're at liberty to kind of change this and to adapt it to what makes us most productive.
So you kind of define a set of directions you want to go into, and then people have liberty to explore these directions in whatever way.
Yeah, actually, this is why I think the Excellence Initiative, which is the program within which the Science of Intelligence is funded, is such an amazing program, because we didn't really have to even set a direction more specifically than saying we want to study intelligence. Mm-hmm. We want to define a new science about intelligence. And then we proposed a number of measures that we would implement in order to guide the activities. And we gave some examples, but if you want to really develop a new science, you cannot predict 5 years out what is going to be the thing that you want to investigate then. So we had very little specifics in the proposal. It was really just about the whole environment and how we were going to structure everything. And I think this has given us the freedom that we needed to get really great insights and results.
Mm. Allow me to sneak in another comment on liberal arts. I think these are similar motives. You can't maybe just like the professor cannot say what precise research direction will be interesting in 5 years. I think the 18-year-old probably can say what he wants to do or she wants to do for the rest of their lives. So I think the idea of like giving more freedom to explore is similar.
So I think freedom to explore is great, but there's also, I think, a mechanism in our brains that once we start becoming good at something, we start liking it more, right? So in some sense, I think you could say that, so I think the other motivation to educate people to be good human beings is actually more important. I think if people just dove into a particular topic that seemed interesting to them at the surface, I think they would love it. They would learn to love it.
That's true. So speaking of things people are good at, you're quite good at robotics. You do something called soft robotics. That's like a field you're in. Maybe first tell us, what is soft robotics? I think it's an interesting term.
Yes, it's an interesting term. And maybe in order to understand why or how that term came about, we have to talk about hard robotics.
Sure.
So robotics used to be hard, in the sense that, I mean, I'm overgeneralizing here, right? But the general approach was that if you want, the brain is going to figure out everything, and then the body is just there for executing what the brain has come up with. So then, if that's the philosophy that you pursue, you want to be able to be able to predict exactly what your robot, what your body is doing when you command something. And that's much easier if you have very stiff, hard links, because you only need to measure the angle at the joints, and then you know where every point on the robot is. And that dominated robotics, I think, since the beginning. And people have tried to make robots stiffer and so on. And this is exactly what's happening in industrial robotics, right? These robots have become bigger, heavier, stiffer. But then people realized that actually might not be the best way to go about doing this. People started taking, well, I should say that people have always said that, I think, all the way from the beginning. People, there were always some people who said robots need to be soft, or being soft is a good idea. But maybe 10, 15 years ago, this started to spread, and people realized that making robots soft, yes, it makes them less controllable. You have less control. You don't know what your robot is doing. But the softness can really help you in doing something. And it has proven to be such a simple but so powerful idea that I think there's a whole new robotics community spawning off. And I really wish that they would not spawn off, but they would stay integrated with traditional robotics. But they have started their own conferences. They have started a new journal, and it's great, right? I mean, these are good things. But I don't like the fact that they're split off, because I think soft robotics is mainstream robotics, right? This is how robots are supposed to be for certain applications.
Do the two ways of viewing robotics, one is hard robotics and the other soft robotics, also correspond to different understandings of intelligence?
I would say so. Well, I would say that, yeah, okay, good question. Not so easy. So what's the benefit of soft? Soft is when you actually, for example, touch the environment and you exert forces onto your environment, but the environment exerts forces back onto you, and that makes you adjust, for example, the posture of your hand. Like when you grasp a glass that's standing on a table, you wrap your fingers around that glass, and you don't know exactly where the fingers are going to come to rest or what the angles in your particular joints are. You just rely on the fact that you have soft pulp on the inside of your fingers that complies to the surface of the glass. And you basically also the kinematic structure, right? The different bones and joints are such that they can wrap around the glass very nicely. And so you don't care about where exactly you grasp it. Your fingers help you in the computation. You don't need to compute what exact posture you need to have. You just pull on your muscles or on your tendons by contracting your muscles, and your fingers do the computation for you. So that's the key. The material performs computation, and that is maybe first strange to kind of put your head around, because we think of computation as something that CPUs do, computers, GPUs, right? But actually, material performs computation. For example, people design bicycles so that they absorb shocks into one direction, right? Like the rear part can absorb shocks in one direction, but is stiff in another direction. So I've designed some functionality into the material itself. And so we can do that with bodies. I mean, our bodies are full of these things. The way we walk is driven by the way our bone structure and the muscles and the tendons are connected to each other. Otherwise, it would be super difficult to walk, right? But now we can use the structure to help us. And so you can view soft robotics as using traditional computation plus a different form of computation, which is performed by the body. So if you have two different paradigms of computation, it seems logical that you have more computational power, right? And maybe another example, we all, quantum computing is in the news, and we all hear that quantum computers are going to have capabilities in some respects far beyond what our traditional computers can do. That's another computational paradigm, right? So just like when you add quantum computing to a normal computer, you get something that can do more stuff. If you add a body to a computer, you can do more stuff. And so, especially in robotics, where the objective is for a machine to change the state of the world, you need a body, and then you might as well use it for something good rather than just to execute what the brain has decided. And I think that taking this shift in philosophy and approaching robotics problems really has brought about changes and progress in many, many ways.
That's also, when you started talking about intelligence, you mentioned like animals as an inspiration. I think if you look at humans, for example, it's quite incredible how much of our actions that we perceive as intelligence, as you described, are done by the body. I think another good example is keeping your balance in some scenarios, which if you do it computationally is absurdly difficult, but humans can just somehow do it. Do you know of any interesting applications for soft robotics, maybe even some that are already being deployed?
Yeah, I mean, especially the grasping, right? I mean, Amazon, for example, is investing huge amounts. They have an own robotics lab here in Berlin, huge amounts of money and personnel into developing robotic solutions for their warehouses, for their, I think they call them fulfillment centers or something, right? You know, both putting things onto shelves and then getting shelves out to assemble the orders. This is something that robots can help with, and they need to interact with a whole variety of different objects, right? I mean, Amazon has tens of thousands of products in their warehouses, and humans obviously can interact with all of them, but developing machines is super helpful for this. We collaborated with a company in the UK called Ocado. They're an online grocery, so an online supermarket, and they wanted to automate fulfillment of fruit and vegetables, right, which are soft, so you don't want to bruise them. They have different shapes. It's not like a can of soda that looks exactly the same or has the same shape at least. So in all of these domains, where the hand can take over some of the details of what you want to do, and you don't care anymore whether the apple has a bump on the side or not, because your hand will take care of that, right? And so I think, you know, soft robotics has opened many new applications. Talking about prosthetics, right? Making more capable prosthetics for people. That's, you know, I don't think that we have really reached that level yet, but people are actively working on making much more dexterous prosthetics for people that don't have arms or hands anymore.
Yeah, I think the examples you mentioned where the robots kind of interact with the actual biological world, so like fruit or humans, those are especially interesting because that's where probably hard robotics runs into many problems.
Yes, a very apt observation, right? I mean, industrial robotics succeeds in scenarios where we can design every aspect of the environment. And so if you go to a car factory, they spend 10 times more money on designing the environment than they spend on the robots that build the cars, right? So such a robot is only a robot in the environment that was designed for it. And if we want to build machines that are not like that, that can operate in the environments that we live in, we need to do something differently. And I think soft is one component, or embodied intelligence, if you want, is one component towards building systems that can do these things.
So to get into more concrete examples of your research, you mentioned the British delivery supermarket that wanted to wanted to grab food or work with food. So if you look at your lab's website or the YouTube channel, there's a lot of videos involving a hand.
Yeah.
And this hand looks very cool.
Yeah.
Tell us, I think it's currently in the third iteration, if I understood correctly.
Yeah, correct. Yeah.
Tell us, what was the first iteration? What inspired the design of the hand, and what has happened since?
Yeah, that's a fun story. So I had nothing to do with grasping or hands or manipulation. Like I told you, right? My thesis was about generating robot motion. And so we had, after I arrived in Berlin, gotten to the point where our robots could move about the environment quite well without hitting things and avoiding people. And so the next question was, well, good, one basic skill check. What are we going to do now? Yeah, a robot should pick something up, should do something, right? Should manipulate the world somehow. And yeah, we tried that. I thought other people had solved that problem, and we tried solutions that people were proposing, and nothing worked. And then I realized, okay, this is not a solved problem. We have to solve it if we want that skill. Then a student was, we had some hands in our lab, and a student was supposed to evaluate which of these hands was better. And I came to the lab, and he was performing an experiment where he was grabbing with the robot hand a large metal sphere that was hollow. So it was very light, but if you touched it anywhere, the energy would immediately, shoot the ball out into some direction. And he put it on a little ring so that it wouldn't roll away while grasping. And I was like, well, that's kind of cheating, right? You don't need that ring to pick up that ball. Come over here, show me how you pick up that ball. And we looked at him picking up the ball. First you spread out your fingers and you try to constrain the ball before you even touch it, so that when you touch it, it cannot roll anywhere because you already have your fingers on all sides. It's like, okay, so you have a strategy that you pursue to counteract this effect that if you touch it, it will just start rolling. And then it was like, wow, I've never thought about it that way, right? Humans seem to be doing this very differently than robots. And then I went into my undergraduate course and I said, I need 10 volunteers for a study on grasping. Just come to the lab and we'll pay you some money. And we're going to record you as you pick up objects off a acrylic, transparent table. And we recorded this, from every perspective. And I looked at these videos for hours, frame by frame, and I had no idea. This was what we observed there was so different from the way roboticists were thinking about it. And that basically triggered a 15-year, I think at this point, or maybe 10-year research program into understanding how humans do this and transferring these concepts and ideas to robots. And that necessitated building hands that are good at touching the world without hurting themselves or the world. And so we started building soft hands. The first one was super, super simple. It was basically a little piece of wood, of plywood, with three, wobbly fingers, in quotes, they didn't look like fingers, attached. And this hand could pretty much pick up anything. We had a video where it repeatedly just grasped without sensing. It just reaches out and closes the fingers. And we could put pretty much anything on the table, it would just pick it up. Mm-hmm. And I showed this to roboticist colleagues of mine, expecting for them to be super impressed. Because, something that without knowing what it's picking up and without doing any sensing is pretty much picking up anything, right? That was the problem that everybody was working on, and not successfully. But people were not impressed. And I was like, well, how can that be? We're solving the thing that they are trying to solve, and why are they not impressed? And then I realized, okay, this hand looks like, well, it didn't look very nice. And I said, let's make it look anthropomorphic. So the second hand, it had various improvements. Rather than only 3 fingers, it had 5, it had more actuation, it could do more things, but it looked like a human hand. Mm-hmm. The next thing is, it wins the Best Student Paper Award at, the top robotics conference. Mm-hmm. Even though that was basically the same thing, just, a little bit
more human.
Exactly. Mm-hmm. So then, yeah. So in that second version, we designed everything for being as soft as possible, but then we realized that we need kind of soft and the ability to control all kinds of things. So then the third version, it's soft, but it still has very, very dexterous capabilities. So it can move the fingers, and even the palm can bend, and the thumb is very capable. So we really put a lot of things in there, and I think this is going to be our platform for studying manipulation for a while now, because it's a really very capable hand, and now we need to catch up in terms of understanding how to control it. Yeah.
If you look at the human hand, it's very complex. It has like many parts.
Yeah.
Can you walk us through the different elements of the latest hands, how you designed them? And also, you're a computer scientist by training. These hands involve a lot of engineering. It seems like engineering from all sorts of disciplines. How did you face that challenge?
Well, I think as a roboticist, you need to be able to pick up things from other disciplines, because robotics combines many things, right? I mean, there are mechanical engineers that are roboticists that really just do mechanical engineering. There are electrical engineers, there are computer scientists. So you need to pick up these things. And actually the engineering with soft robotics is pretty simple, which is another advantage, right? We can build a hand in a couple of hours, where it would have taken months to build a hard hand. Everybody needs to pick up these things. There's just no way around it. So to walk you through the different components, I think the most important thing is the thumb. And the thumb is also what distinguishes the human hand from the hand of other primates, in the sense that it can oppose all the other fingers. You can really put the thumb in opposition. So that's important. And so in the base of the thumb, we have 3 different actuators. That really, so there's 3 degrees of freedom that allow us to position the thumb relative to the rest of the palm. And then the thumb itself also can bend. The fingers, all 4 fingers without the thumb, kind of have 2 modes in the human hand. One is that they can bend at the very first joint while staying straight. And then they can just bend as a whole with the second and the third joint. And as a human, you can kind of almost control these things independently. So we've built fingers that can do the same thing. Then you can spread your fingers apart, right, and move them back together. That's also something that the hand can do. And then it turns out that you can actually, in the middle of your palm, you can almost move the little finger towards the thumb, right? Just a little bit. So if you wanted to speculate from an evolutionary perspective, maybe the little finger is beginning to develop into a second thumb. Because it would be actually very useful to have a second thumb. And people have built attachments to human hands where you add a 6th finger that acts as a second thumb. So, and then something that you cannot forget when you look at the hand is the wrist. Right, so it turns out that when humans use their hand, the wrist movement, which involves the whole arm placing and leading the wrist through the environment, is highly coordinated with what the fingers are doing. And then the whole thing about materialness, right? I mentioned the pulp before. The pulp has amazing properties of complying to objects, but in other situations, when there's a large surface contact, kind of becoming a good frictional pad. So the pulp, actually, there's a lot of evolutionary smarts that went into that design. Another thing are the tenons on the inside of the human hand, and we don't really actually know. We don't have a precise model of human hands because it's actually so complicated. I always thought that the tenons that actuate the fingers are like strings. But they're actually like sheets that are interconnected. And so the ring finger and the little finger usually are more connected than others. And when you play the piano, being able to control these 2 fingers independently is a super big advantage. Yeah, so the hand is a complete marvel of evolution. And I would not say that we fully understand all the tricks that are in there. But looking at the obvious tricks and transferring those into the robotic realm already, I think, has been a game changer. So yeah, I mean, you could say that going bio-inspired is a good idea. But I think we have to be careful not just to copy the exact biology, but we have to understand the principles.
That's super interesting. One, I think I've never thought of like the different functionalities my fingers have and how you can combine them. That's super cool.
Isn't that beautiful, right? I mean, you are a machine for grasping.
Yeah.
You can do this without any conscious effort. And when you do that, your whole, you can do like these fMRIs where you see which regions of the brain are circulated, more actively than others. Grasping and manipulating the world is one of the most challenging, if you want to use it as a measure of being challenging, things that we do. The whole brain lights up when you do that. When you do math or when you solve some, play chess, just some areas light up. But when you manipulate, the whole thing is glowing. So we do it effortlessly, apparently, but there's a lot of computation underneath that's going on.
Yeah, cool. Maybe that's the reason it's much harder than other things this type of intelligence to automate, because evolution is just so good at it.
Absolutely.
Has made us so good at it.
So, and this is not news. Hans Moravec, was an Austrian, I think, at MIT, professor at MIT. Already in the 80s, he coined this expression that's called Moravec's paradox, that the things that are easy for us to do a computer are hard for humans, like playing chess. But the things that are easy for a human, like manipulating or facial recognition and so on, are super difficult to do on a computer. So yeah, I mean, we've been focusing on the wrong kind of intelligence in some sense. And I think the body has been underrepresented in our efforts to try to understand human intelligence.
So the hand also has a lot of sensing capabilities.
Yeah.
Especially, that's also something when you play instruments. I think if you play the violin, it's super important to like have this close contact with the strings and really feel it. How do you tackle that challenge?
Yeah. So first of all, I think it's important to say that it's amazing how many things you can do without sensing.
Mm-hmm.
Right? I mean, we get trained on grasping manipulation with sensing. And so if you take our sense away by anesthetizing a nerve or something, we fail, of course. But if you take different strategies, you can actually do a lot without sensing. Having said that, sensing is super important. And when you make soft hands, it becomes problematic because all the sensors we have are hard. They need cables that go to the sensor and lead signals back and forth. And we want to have softness. We want to have compliance. If we now start embedding all kinds of electronics into the hands, they become hard again. Mm-hmm. So we had to also develop some new technology for sensing. Mm-hmm. And we developed actually 3 different technologies. One of them that's kind of fascinating, I think, is acoustic sensing, where we actually embed a loudspeaker and a microphone inside the finger. Mm-hmm. And the loudspeaker makes a sound. It's barely audible from the outside. It's just inside the finger. And the microphone records it. And, how is that a sensor, right? I mean, that seems kind of strange. But if you imagine a guitar and you play the strings, and then you fill that guitar with water or with sand or with apples, or you cut off the back plane of the guitar, it's clear that the sound will change. So the way the sound that's emanated from the strings gets modulated by the body of the guitar reflects the state of the body. And so we do exactly the same thing, right? The sound that the loudspeaker makes gets absorbed and modulated by the whole finger, and then we record that modulation. And from the modulation, we can reverse compute what the state of the finger is. And that includes how warm the finger is, where there's contact with the finger, how many newtons that contact is, how many contacts there are. We even have made a finger that can read Braille, right? I mean, from a human Braille display, with an accuracy above 90%. I think that's, on a letter basis, which I think is, kind of human level performance.
Wow. How accurate are the temperature measurements?
Oh, I don't know. Probably within a couple of degrees. So it's not good as a thermometer, but it's good if you hold your hand into a fire, right? You will find out.
And how do you connect the measurements, like the different acoustic attributes, to the senses? Do you like just collect large amounts of data and then
Yes.
like train some
Yes.
machine learning
Yes.
models?
And these machine learning models, surprisingly, are very, very simple.
Mhm.
Yeah. So the sound that we record, right? We do a Fourier transform, and then we get these histograms of frequencies, and we even integrate over time. I mean, we're even not using the full information that's in the signal that we record, but we really had a difficult time finding something that we couldn't sense. Right? It's really astonishing. Yeah, this was really something. So the first time the student came with the results, even though I had suggested that we should do that project, when the students came with the results and the results were good, I said, you know what, I don't believe this. And the student was like, yeah, this, it seems crazy. I also think I made a mistake. I don't know what happened, but these are my results. And I said, well, what do you think? Should we just, or should you just re-implement it from scratch? Just everything from scratch, record the data, everything, just to see if the result is the same. He's like, yeah, I think that's a good idea, because he was worried, to publish something that was,
It's too good.
yeah, well, yeah, that's just not true, right? And so he re-implemented it all, and yeah, the outcome was the same. And then we tried more and more challenging problems, and it always worked.
How much data do you need to train these models, and how do you gather the data?
Yeah.
Is that difficult?
And so it's actually not that much. So compared to deep neural networks or something, we need millions of training data. This was a couple of hundred test samples. And we generate it by putting the hand or the finger on a robot, and then the robot goes through a certain test sequence of states and records the measurement in that state, and then that's it. So we automate and it just runs unsupervised. We gather the data, and it's super simple machine learning. Like most of the things we did with k-nearest neighbors, which is the simplest thing, and then where that kind of led to not 95% success rate, we then switched to support vector machines, but we didn't have to to get the big machinery. It was very simple.
I really like the idea of achieving a lot with methods that seem simpler than others. Maybe this is something that you can do with soft robotics and like all kinds of
Absolutely
problems. That's super cool.
Absolutely. And you're raising an interesting point, because I think in science, complexity is still appreciated when simplicity should be what's appreciated, right? Yeah, I mean, so I totally, to me, if I show our research to somebody and they say, okay, this is so simple, I could do this, it's like, yeah, that's exactly the point, but you didn't. Yeah. Right? It solves the problem, it's super simple, you had to have the idea, right? But then the realization is easy. And that also leads to robust solutions often, right? I mean, most often.
I like the way of looking at it, where if you do very complex seeming science, everyone will be impressed by your intelligence. And if you do very simple seeming science, and you can make everyone else feel kind of dumb for not inventing it themselves.
Exactly.
This is so simple. Why did you not come up with this?
Well, but this is I think, especially in a field that's so new as robotics and AI are, right? And physics, I think it's difficult to come up with something simple that will, make people think like, oh, why didn't I come up with that, right? But in a field that's this young, it should be the case that these things still exist, and they do.
Look for the simple things.
Yeah, absolutely.
Bring a lot of value. Yeah. Wow, it's super cool, super inspiring stuff. Maybe to help us come up with good new ideas and new simple things. I always ask my guests for book recommendations. Ideally, I would like to hear, but if if you can't provide that, that's also perfectly fine. One book from your field, so maybe a good textbook that talks about soft robotics. The second thing is a book that is related to that is a scientific book that is not directly related to your field, so it could be something you read about biology you thought was cool. And the third thing is just any book you think is inspiring.
Okay, I mean, I'll try. So there are no textbooks about soft robotics because the field is so young. And I don't think there are even kind of modern books about robotics. Most books take very much the traditional approach. If I had to recommend one textbook on robotics,
it could also be, I think if it doesn't have to be a book. If there's a YouTube video or something you would recommend people to watch if they want to get a good grasp of soft robotics, or a website or an ebook or a course.
So there's a website, I think it's called the Soft Robotics Toolkit, where all these simple solutions that you come up with in the beginning of a field are collected, explained, and with papers and CAD data. And so if you wanted to start playing around with soft robotics, I think that would be a good place to start to get inspired.
Cool. So book number 1 is a website.
Yeah. Cool. Okay. So if you let that pass, then that's great. The second one was something
science related, but not soft robotics or not robotics.
So there I could give you a whole list of things. And some of these, maybe don't age so well, but I really like to read from other disciplines like neuroscience or biology, kind of popular science books, because they give you like a big perspective.
They tell a good story.
They tell a good story, but also from somebody who knows how to tell the story, in the sense that they have so much experience that they don't just give you the facts, they give you the facts in perspective. And that perspective, I think, is invaluable, especially for somebody who researches with connections to that field. So one of the books that I read a long time ago that really blew my mind and kind of triggered my going into the biology direction was a book called Alva Noe, who I think is a philosopher / neuroscientist, which is called Action in Perception. And it's making the argument that perception is not a passive process, but it's very much comparable to tactile perception. You actually have to go out and sample the world. And this came at a point when we just coined the term interactive perception for this idea that robots, in order to perceive the world, need to touch the world, because when you touch the world, you create new visual signals that wouldn't otherwise be there, right? Like you could never discover a door if you didn't try to open it. So that is one, I think that, but that's, I read that at least 15, 16 years ago. So that's a long time ago. And then current books that, I assume you're not asking for like fiction or something, right? You're asking for...
the third question is any book. So it could be fiction, it could be poetry, it could really be anything. Okay. Can I also say several? Sure.
Because, if it were poetry, if you're German, I would really recommend by Rainer Maria Rilke, Du Nese Elegien, which is beautiful and sad. But let me give you also the book that kind of rocked me most recently in kind of the nonfiction category. It's a book by two people. I only remember one author. His name is Jonathan Haidt, and the book is called The Coddling of the American Mind.
Okay.
Have you heard of it?
No, unfortunately not.
So, not that is necessarily good advertisement, but Bill Gates has it on his list of the 8 most important books ever published.
Oh wow! Okay.
And I came to read this book because I noticed that somehow the attitude of the students that are coming in now are changing relative to the students I had taught for the last 20 years.
Mm-hmm.
And I was trying to understand, what the source of this is. And I think this book, Jonathan Haidt is a psychologist from Columbia University, so he's a scientist. This book gives some interesting answers that I think are important for us as a society to be aware of, because we're facing some important problems in our times, and we need the next generation to be raised and trained to be willing and capable of confronting and solving these problems if we want the species to persist. So that I think was very that book for me put many things in perspective. Wow. And I think I understand better why the things around me are happening the way they're happening.
Wow, high praise. Now I really want to read that book too.
Well, you only can be disappointed after that praise, but I had to tell you how it affected me.
Fair.
And you have to realize that I'm a couple of months older than you, and to me, things that happened 2 generations after me might seem more mysterious than they are to you. Yeah. So the enlightenment that I derived from that might not be any news to you.
Yeah. Well, thank you, Oliver. That was super interesting. Thank you for taking the time.
Thank you for having me. Research. Really appreciate it. Thanks.
Thank you so much for listening to the Thinkers and Makers podcast. If you liked it, please like the episode and subscribe to the podcast. And if you want to support me and my work, check out the books that Oliver recommends using the links in the description. Enjoy the rest of your week and see you next time.